All right, let's just dive right into this explainer and unpack the absolute magic behind the screen you're looking at right this second. Today, we're tracking a pretty incredible journey. We're going from humanity's humble wooden counting origins all the way to those microscopic silicon brains that are literally powering our lives today. Because to truly understand how that wildly powerful smartphone in your pocket actually works, we first have to step back and ask a pretty mind-bending question. How exactly did we transition from carving numbers on strips of bone to casually chatting with self-organizing artificial intelligence? Here's the roadmap for our explainer today. We'll hit the evolution of the computer, classifying modern machines, the anatomy of a computer, peek inside the CPU, and then wrap it all up with memory and multitasking. All right, Act 1, the evolution of the computer. Let's look at the absolute earliest physical solutions we came up with to calculate data faster. Long before electricity was even a thought for computing, we had the Abacus. Developed in China, this is widely considered the very first calculating machine. It's a brilliantly simple yet highly effective mechanical device that uses sliding beads to count, add, and subtract. The centuries that followed brought some major leaps. In 1616, Sir John Napier literally carved numbers onto strips of wood and bone just to handle multiplication and division. And then shortly after that, in 1641, Blaise Pascal rolled out his wildly popular mechanical calculator, the Pascaline, which was designed specifically for addition and subtraction. Now, what's truly staggering here is the explosive pace of the 5 modern computing generations. We jump from the late 1930s, where machines used low-level machine language, just endless zeros and ones, all the way to our current 5th generation today, which is totally focused on natural language recognition and self-organizing artificial intelligence. But early computing looked vastly different. Check out these massive, heat-radiating, incredibly expensive electronic vacuum tubes of the first generation. Computers like the UNIVAC and ENIAC relied on these as switching components. They took up entire rooms, they were a total nightmare to program, and get this, they couldn't even multitask. When we compare that first generation directly to the 4th, which kicked off around 1970, you can really see how our desperate need for speed and efficiency just drove innovation off the charts. We went from room-sized behemoths to cramming thousands of integrated circuits onto a single microscopic silicon chip called a microprocessor. Plus, we finally ditched those endless strings of zeros and ones for high-level programming languages. Using the actual English alphabet and math symbols made software development immensely more accessible for everyone. Moving into Act 2, classifying modern machines. Let's categorize the wild landscape of computers that surround us today based on their size and speed. The crucial takeaway here is scale. A microcomputer is built for one person at a time. Think your desktop, your laptop, and yep, that smartphone running a mobile OS. But when we scale up, way beyond your desk, we hit mainframe computers. These beasts can fill entire rooms, store enormous amounts of data, and talk to many users at the exact same time through terminals. But at the absolute peak, we've got supercomputers. The big difference is that while mainframes juggle a bunch of different purposes for massive companies, supercomputers are hyper-focused. They're built for lightning-fast calculations dedicated to a singular, massive task, like predicting complex weather patterns or doing nuclear research. All right, Act 3, the anatomy of a computer. We are zooming all the way in to open up the modern microcomputer and see exactly what makes it tick. At the end of the day, every single computer system really just boils down to 3 functional components. First up, you have peripheral input devices, like your keyboard, mouse, or even a barcode scanner, and these feed raw data right into the system. Second, the central processing unit jumps in to manipulate and process all that data. And third, your output devices deliver that processed, polished result back to the outside world. Let's push into Act 4, inside the CPU. We're going to look at how these core components build the true engine of your machine. The central processing unit is the undisputed brain of the computer. It's governed by an internal clock where faster ticks, which you usually hear expressed as megahertz or gigahertz, mean more instructions are getting executed every single second. So think of this brain as a highly organized workspace with 3 very distinct departments. The arithmetic logic unit, or ALU, is basically your mathematician. It does all the heavy lifting and decision-making. Then the control unit acts as the floor manager, carrying out program instructions and directing the precise flow of data from input to memory to output. And finally, the memory unit. That's your nearby filing cabinet where data is stored and kept instantly accessible to the CPU. And I've got a pretty fantastic fun fact for you about how this memory unit actually stores your data. So we all know that the most elementary unit of memory is a binary digit, right? A bit, which is just a 0 or a 1. And you've probably heard that a group of 8 bits makes a byte. But did you know a group of exactly 4 bits is officially called a nibble? You can't make this stuff up. Finally, let's move to Act 5, memory and multitasking. We're going to explore how primary memory functions, and specifically how it lets you do a million things at once on your device. So primary memory dictates the amount of data a computer can actually process at any one time. When we put RAM and ROM head to head, you'll see they come in 2 totally distinct flavors. RAM is volatile. It's your temporary read and write workspace. When you turn your computer off, the RAM completely clears out. ROM, on the other hand, is non-volatile. It permanently stores your computer's built-in instructions, and it definitely does not forget them when the power drops. Which naturally leads us to a crucial question about something I guarantee you do every single day. How exactly does your computer juggle streaming music, running a browser with 20 tabs open, and saving a heavy document all at the exact same time without completely freezing up? Well, the secret sauce here is RAM. In a modern multitasking operating system, when you open up multiple apps, RAM acts kind of like your wide-open disk space. It temporarily holds all that active data right there so the CPU can just switch between those tasks in a fraction of a second without you noticing any delay whatsoever. Because without RAM acting as this lightning-fast intermediary, your CPU would be forced to constantly fetch data from your permanent secondary storage, like your hard drive. And trust me, that process is incredibly slow. It would instantly turn your speedy, modern workflow into a sluggish, unresponsive nightmare. We have zoomed all the way from those giant, hot, room-sized vacuum tubes of the 1930s to the microscopic, multitasking processors we carry around in our pockets today. But knowing that developers are currently knee-deep into the 5th generation, building artificial intelligence capable of actively organizing itself, it leaves us with one pretty wild final thought. What on earth will the 6th generation of machines look like tomorrow? Thanks for hanging out with me on this explainer, and I'll catch you on the next one.